So we want to see where this times this is greater than or equal to 0. And we certainly know that it equals 0 at negative 4 and 5, right? Negative 4 plus 4 would give me 0, and that would make the whole thing 0. And 5 minus 5 would be 0, and that would make the whole thing 0. So I know where it's equal to 0. Those 2 points certainly will be part of my solution. And there are lots of other points, right? Like if I plug in maybe 100 minus 5, that would be 95. 100 plus 4 would be 104. That times that will certainly be positive, right? So it turns out that these zeros are going to help us figure out where it changes from positive to negative. Because if you can imagine the graph, if you've got a graph that equals 0 at negative 4 and 5, if those are the only 2 places it equals 0, and those are the only 2 places where your function can change signs. So imagine, and it's not going to be what this is, but imagine your function starts down here, and then it equals 0 and it crosses, so it was negative all here, and positive up here, and then it's positive, 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 and then it tries to dip down to being negative, but oh no, it can't equal 0 there. So it's got to wait and wait and wait and wait, and then when it hits 5, it has the choice. It could either bounce back up and stay positive, or maybe then it can cross and stay 0. So these zeros are the only places where your function can change from being negative to positive, or from positive to negative. It has to cross this axis first. And that's your intermediate value theorem. So you'll get to that later. But yes, so these zeros are crucial points. And so you throw those on a number line, and then you figure out what's happening over here, here, and here. So it's either like all negative for things that you plug in bigger than 5, or all positive. So my teachers always used to do the pick-a-point method. So you would pick any point that you wanted greater than 5, and my teacher always used 1 billion, and I didn't understand it then, but I totally get it now, because you don't care what the actual number is, you just care whether it's positive or negative. So if I plug in 1 billion, so I'm plugging in 1 billion over here, 1 billion minus 5 is certainly positive. 1 billion plus 4 is certainly positive. A positive times a positive is positive. So I'm definitely going to be positive over on this side. And then they would have us plug in points beyond and between, they would call it. So then they would go and plug in something between negative 4 and 5. So they were like, oh, 0 is between negative 4 and 5. So let's do it again, and we'll plug in 0. And 0 minus 5 is negative, and 0 plus 4 is positive, and a negative times a positive is negative. Okay. And then, so it's negative between there. And then over here, anything beyond negative 4, like a negative billion. Negative billion minus 5 is negative. Negative billion plus 4 is positive. No, negative billion plus 4 is certainly still negative, sorry. Negative times a negative will be positive. So now you know that for any x, you can try it, any x you plug in less than negative 4 will make this thing positive. Any x you plug in between negative 4 and 5 will make this thing negative, and anything x you plug in beyond 5 will make it positive. And then you're like, okay, that's great, but what do I want, right? In this case, I want this to be greater than or equal to 0. So I want the positive. So I want all of these and all of those. And I'm going to write my answer, negative infinity to negative 4. So, and then I can include the 4, so I'll make that a bracket. So I'll take all x's between negative infinity and 4 and unite those with all x's, 5, including 5, all the way to infinity. And that's how I'm going to describe my answer. Those describe the x's that'll make this work. Phew. Okay. One more thing I want to say, and we'll get through them a little bit faster as we go along. But you'll notice that they tend to alternate, right? This is not a coincidence. If you plug in things like this guy here, if you plug in things slightly bigger than 5, that's going to make this positive, this whole factor positive. And if you make things slightly smaller than 5, like 4.9, 4.9 minus 5 is negative. So right around the 5, this is going to change, right? It's going to change from being positive to negative. That's going to affect the the result. Now, we'll get to it later, but so you can safely say if these are to odd powers, it's going to change signs. Once you find one, if you're confident you found that this one was positive, go ahead and alternate it down. I never did it when I was in school, and it was silly. I should have. Now the tricky part though comes in if this were squared, which we're going to run into later. If that were squared, it wouldn't matter whether this thing was positive or negative. The thing is always going to be positive, right? Doesn't matter what that is. If you're squaring it, it would be positive all the time. So it's not going to change signs whether on the right side of 5 and on the left side of 5. So sometimes when I do that, I'm going to put a little star on anything that has an even multiplicity, because even if it were a 4 or a 6 or whatever, that's going to stay positive. So I'll put a little star, and then as I go down, I'll stay positive, or the same sign that I was on the other side. Anyway, that'll make sense. We're going to get into a groove. The first one's always just a little bit longer. Okay, here we go. On to the next.